to unified conferencing.
Free laminated sheets are here, huh? Are these ready to pass out?
Yeah.
Wow. There's 4 of them?
Yeah.
And you guys are spoiled. So what do we do? Get these out now or wait?
Whenever. Pick them up whenever they want, now or at the end of class.
We got 5 minutes, so if you want to start, just pass these out to everybody. Take one from each folder. Can you believe 3 years has gone by already?
User, can you adjust the camera to the right?
Alex, can you see it?
Yeah, I just need the last two panels on the right.
Okay.
Okay, it's 8 a.m. Can you guys hear me in Florida? Yes? Okay, great. Well, welcome to Heterocycles 2019. A few notes before we get started. 2019 is the new and improved version, so there's been many iterations. This has been a class for over a decade now. So a few things we should talk about before we begin. First is the notes. Why are we still writing on a chalkboard? It's obviously harder for me. It'd be much easier just to read you bedtime stories from a PowerPoint presentation. The point is that you don't commit much to memory if you don't write it. So that's the point of putting the stuff down. The other point is a more pragmatic one. When you have the exam, which is quite a torturous event, the exam will be open note. So anything you write on paper, you can bring with you. So if you want to take Jewell and Mills and write it, the entire book by hand, you're welcome to do that. We haven't had anybody do that, but you can do it. The point is just to get you to learn the stuff. So this is a sneaky way to do that. For 2019, we introduced espresso. And you can have some if you want, but the rules for engagement for the espresso are essentially class participation, which can actually earn you quite a bit of points on your exam. So to encourage participation and a lack of yawning, by the way, if the TAs catch you yawning, It's a -1 espresso credit. You'll have to get yourself back out of that ditch if you fall in. We're going to assign this year, and you might want to pair up with these folks for future classes, sit next to them. We're going to have, for the people who are taking the class for a grade, even the auditors will be involved, but the people who are taking class for a grade are going to be in teams that their goal is to be the heterocycle master of the particular class they've been assigned to. So Dongmin and Steve, you are now Team Pyridine. You better sit together. Alex, Saul, and Zheng, Indol. Pyrrole, Max, and Max. Imidazole, Chang, and Nick. Quinoline, Hannah, and Vincent. Pyrazole, Elena, and Lucas. We've got the diazines. So the pyridazines, pyrazines, and pyrimidines are going to be Tucker and Jess. And then we've got the benzoannulated furan and thiophene. That's going to be Shuang, Sarah, and Ziji. And we've got oxazole and thiazole. It's going to be Zoe and Ziki. And we've got isoxazole and isothiazole. It's going to be Teho and Han. Pyrones and berylliums. That's going to be Xiaokun. Now the auditors, people who are taking this class for just auditing, they're going to be the number police. So we've got Tanner, who's going to be in charge of our pKa values. Thank you. And we've got the aromaticity police. That's going to be Khalid and Nicholas. So you two are going to be in charge of knowing everything about aromaticity. Okay, great. So class adjourned. Oh, no, never mind. No. So first thing we're going to talk about, the next 3 lectures are all going to be about basic reactivity. And, the goal of the class is really to get you ready for drug discovery. Or maybe you're going to go into agro world. But we have a lot of stakeholders that we need to make happy in this class. Because some of you are going to go on to medicinal chemistry. We want to keep you happy. Some of you are going to go into process chemistry. We want to keep you happy. Some of you may become radiochemists. Different logic there. And some of you may say, to hell with it, I'm going to do patent law. And we're actually going to have parts in the class that address that as well to make you happy. We've also got some local heroes from drug discovery. So if you're from a company, can you raise your hand? Fantastic. What company are you from, sir? Oh, Lily. Wow. What's your name? Ren. Okay. And Patrick, right, from Pfizer. So you guys are going to be in charge of filling those boards every morning. Now, I know the industry folks are like, wait a minute, what we do is secret. We can't do that. But most of the consulting problems you guys have are actually very generic ones. So whatever you can bring every class and put it on there, it doesn't matter what it is, I'll turn it into something which is appropriate for the lesson. It doesn't matter what. My Suzuki coupler doesn't work. I don't care. Just put it up there. The goal is one day you'd go on to the noble mission of doing what they're doing. They say, those who, you can either... those who can do, those who can't teach. So I can't do anything. But those folks are the ones who tell you that what we're actually learning here are valuable ideas. And people I've talked to who have gone on to companies have said this is probably the most valuable class they've taken. All right, so there's 4 main classes of heterocycles. You've got a benzene ring, which is very boring. And then you add nitrogen, and all the fun starts happening. Okay, so you can take a benzene ring, excise a CH bond, and throw in its place a nitrogen. And what happens from that is you get these pi-deficient heterocycles. And the pi-deficient heterocycles come in 2 flavors. You've got the ones that are just with 1 heteroatom, and then you've got the ones that you start twinkling in more heteroatoms, 2, 3, sometimes even 4. 5 and 6 we're not going to cover, for obvious reasons, unless you go into the military and start doing energetics. Okay, now if you take benzene ring and you take out a CC bond and throw in its place a nitrogen, now you get what's called pi-excessive heterocycles. And these are generally upset with life. They're often just angry. And I'll get into that in a minute. I like to apply these anthropomorphic characteristics to heterocycles because it's just a pragmatic way of remembering how they react. So you can add 1 heteroatom, and it's just a pyrrole or a furan or a thiophene, or you can add multiple. We will cover the azoles. There's teams here that are now in charge of learning everything about azoles. And we're also going to cover triazoles, and yes, we will even cover tetrazoles. These are pi excessive. The two types there are one heteroatom, and then when you start adding more, is another type. So aromaticity is a useful way to predict everything. So if you understand relative, and I don't mean you need to memorize what is on, it would be helpful to commit to memory the general features of what is outlined on your laminated sheet, which you can bring to your exams, by the way. But if you go to the book, which I think everybody's got, the grad office has kindly agreed to pay the exorbitant $10 to fund all of the folks access to the book. And within that, you see in the laminated sheet, you've got these heterocyclic aromaticity values, which I have to say are a cause for some consternation and debate in literature. The general trend holds, but there are exceptions for these. So the general trends are pretty intuitive. Okay? And if you understand aromaticity in a general sense, the idea is that you will be able to predict reactivity on heteroaromatic systems that you've never seen before. That's the whole point of the class. So reactivity, of course. Tautomerism, what is tautomerism? Anybody know what that is? Any clue? Max, any clue what that is?
It's just like different structures and different proton positions.
That's it. So two structures that only differ by a proton position. That's it. It's kind of important to know that for reasons we will get through. You'll see it almost every class. The reactivity of substituents. So not all methyl groups are the same. A methyl group on a pyrrole, big difference than a methyl group on a pyridine. And it's all about knowing the aromaticity. And then even retrosynthesis. What do you mean by that? Well, now that we have teams, it means we can have heterocyclic UFC cage matches in this class. What do I mean by that? Have I lost my mind? Well, if you look, for example, at the book here, you see there's this chapter on 5,6 fused heteroarenes. And the question becomes, we're going to talk about this a lot, how do you know when you have a system like this, that most of you have probably never seen before, how do you know which one to disconnect first? Do we go this way or that way? Well, when you guys fight it out, brawl it out, you're going to need to know aromaticity to know which one do I make first or second. Okay, so not all nitrogens are created equal. That's a really important thing to remember. And we're not going to get into orbitals and homolumo coefficients because it's not really needed in drug discovery. You can look that up. What you really need to know is the intuitive, the hound dog sense of reactivity. And what you need to know here is that there's two types of nitrogens. Really easy to remember. You've got pyrrole nitrogens and you've got pyridine nitrogens. Here they are. So pyrrole would love to give away electrons. It's pi excessive. And that's why if you have a pyrrole, it often will just react with air. It will react with protons. It will polymerize. We'll see that tomorrow. Pyridines, however, are relatively stable. They're not as aromatic as benzene, obviously, but they're closer. Pyridine is what I call the schizophrenic heterocycle, because embedded within it is a lot of things. So pyridine, when I look at pyridine, I think, okay, there's nitrobenzene in there. So I view this as a sort of version of this. So in my mind, when I see pyridine, I see that. I also see this. And imine. What else do I see? I see this. All three of those things together amalgamate in my head when I see pyridine like nitrogen. Triethylamine. What does triethylamine do? Likes to attack things. Makes adducts really well. Acts as a general base. What's an imine? Well, it likes to electrify. You can add things to an imine. And nitrobenzene, generally just electron deficient. So it doesn't do Friedel-Crafts very well. All of those things are inside of a pyridine. Now, what happens, somebody, and I won't call them out, asked this great question of this dichotomy that exists. So if I start adding nitrogen, more nitrogens to pyridine, if you look at the aromaticity values on your laminated sheet, if I start taking pyridine and adding more nitrogens to it, it becomes less aromatic. That's okay. But if I take pyrrole and I add nitrogen to that, now it becomes more aromatic. And that seems to be like a paradox, right? That doesn't make any sense. But all nitrogens are not created equal, and all ring systems are not the same either. There's a big difference between taking a pi-excessive heterocycle and adding a nitrogen to it, than taking a pi-deficient heterocycle and adding even more nitrogens to it. So as you can imagine, trinitrobenzene, not as stable as nitrobenzene. And if I take a nitrogen and add it to pyridine twice, I get triazine, which is actually, if you start adding substituents, triazines are energetic molecules. Some of them, like nitrotriazines, you can use that in propellants, explosives, whatever. So why is that? Well, the reason is clear. If you take a pi-excessive heterocycle that has a different, from an orbital perspective, is a different type of nitrogen than that type of nitrogen. If you take one, it's already not very happy. I told you it's angry. Now if we add to this one nitrogen, this is a pyridine-like nitrogen, and this is a pyrrole-like nitrogen. And the pyridine-like nitrogen stabilizes the pi-excessive character of a pyrrole. It's that simple. Whereas if you take a 6-membered ring, and you start adding more heteroatoms, it becomes less and less aromatic. So aromaticity cannot be viewed as simply the additive effect of many nitrogens on the same ring. It's context dependent. That's the key to remember. Aromaticity and nitrogen is context dependent. And so if you've got an unhappy heterocycle and you start adding nitrogen to it, it may become more happy. And if you've got one that's kind of reasonably chilled with its life, like a pyridine, and you start adding nitrogens to it, you're disrupting it a little bit, so it becomes less and less aromatic. Now, this question also comes up. These three folks, which one is the most aromatic? And the literature has got answers for both. But I think that the easy way that I like to remember it is by thinking about what they call topological charge stabilization, which is, probably you don't need to remember that. But if you want to understand why literature suggests that pyrimidine is more aromatic than pyrazine, which is more aromatic than pyridazine, one way to think about it is exchange of carbon for a heteroatom. So, on pyridine, folks, which is the most electron-rich carbon? Let's label them. 1, 2, 3, and let's go to team pyridine. Okay, Dongmin and Steve, which is the most electron-rich heteroatom on pyridine? 2. If I take nitrogen and put it in its place, charge topological stabilization tells me that this one should be the happiest because I did that. Okay, team pyridine, what is the next most electron-rich?
1.
And only one left. So 3. So that means this one should be the next most. And then the least aromatic of these should be the pyridazine. But if you look at your heteroaromatic beta values, they're almost the same. If you can look in literature, you'll find it's kind of on the edge. It's questionable which one is the most. But that's the general rule. In terms of reactivity, that actually helps me understand and predict a lot of reactivity. If you just remember that little rule, it actually helps. So it's really important to remember this we will get over. We will do this over and over and over again. We will be talking about the different types of nitrogens in molecules. So you really need to commit this to memory and try to understand it really well. And to aid us in our understanding, we're going to go through how aromaticity changes a variety of different things. For example, let's talk about the tendency to give addition rather than substitution, which increases as aromaticity decreases. Now, this is intuitive, I think. So let's take a look at problem of the day number 1. Problem of the day number 1, hopefully someone will solve for us. We will pass the iPad to someone. And maybe to start us off, team pyridine. Do you guys need coffee? Okay. So David or Yuzuru will pass out the iPad to you. You can just use your finger to solve it, and we'll all be able to watch in real time as you struggle. Bromine and oleum. What is oleum? It's really strong H2SO4. It's got fuming SO3. It's a disaster. It will it's like battery acid, okay? Really strong stuff. So in your mechanism, you can use protonation or you can use an adduct with SO3. Either is fine by me, okay? You're just going to use a proton. Okay. Maybe we should bring a stylus next time for them. Yeah. Now, while they're doing that, it would be nice if the maxes could be thinking about the alternative case with bromine. And maybe also we might use Team Indol, Zhang, Saul, and Alex, and think about what would happen with the same type of conditions with that. All right, so what have they done here? They have added BR2. Okay, so that's... Oh, they're just going to put two bromines down? Okay. That's good. All right. So thanks, Team Pyridine. So how about Saul and Team Indol? Where first, would you use those conditions for bromination?
No.
Why not? You don't like battery acid?
Because it will go with MBS and no other acid.
Yeah. In fact, you don't even need. You can use NBS, but here's the funny thing: you can actually use a pyridine-based. Pyridine tribromide is a brominating agent. It's, kind of comparable reactivity to NBS. And it can be used to brominate. So it's funny, we need to use these strange conditions really harsh conditions to brominate pyridine, but we can use a pyridine-based halogenating agent to halogenate indol or pyrrole. Now, Saul, where does it go with the indol? Where's Team Pyrrole, the maxes? Where does it go there?
C2.
And what kind of, do I need, what would happen with these heterocycles if I were to dissolve them in battery acid?
They would polymerize.
They would polymerize, and we'll talk about the mechanism of that tomorrow. Because they are pi excessive, and you've exposed it to a situation where a highly oxidizing environment. So you don't need that. Just need neutral, really mild conditions are fine. Why does it go C2 with pyrrole and C3 with an indol?
It's kind of like a vinylglycinamide.
Which one are you talking about?
The pyrrole.
Is kind of like a vanillogous imine.
Or enamine, sorry.
Enamine. Right. I mean, so I think the way to, you can commit this to memory, but you can convince yourself of this when you draw the resonance structures that arrive from either capturing an E at C2 or capturing an electrophile at C3. Draw those, and you'll find there's more resonance structures that stabilize C2 capture. And in the case of C3, you have to disrupt aromaticity for indol. So it prefers C3 to just keep everything cool with the benzene ring. We don't want to disturb that if we can avoid it. Questions? Please don't do Friedel crafts with pyridines. We see this every year in the midterm. Okay? You can do a Friedel crash with a pyridine, but you got to have a donating group on it. Like an amine is okay. Some methoxy ones will do it. That's fine. But we see a lot of people taking, for instance, nitropyridine and treating it with NBS, and somehow a bromine goes on there. You're not going to get the job, folks, if you do that during an interview. It's over. They just close the door, you go home early. Don't do it on a test. Okay. Cyclic transition states reactions. So basically, just think of paracyclic reactions. This one's easy to remember. The rate of those increases as aromaticity decreases. This is rather intuitive. Like, look, if I take a mixture of all three of these things and dimethylacetylene dicarboxylate, which one's going to react? Sorry, who said that? Let's see here. Were you on? Oh, so Max here, you're on the pyrrole team, but you're actually giving an assist to the furan people. It looks like the furan people don't even have a team. I guess it's the. Oh yeah, they do. Shuang, Sarah, and ZG. So you can thank Max for that assist there. So furan is just going to form rather quickly an adduct. In fact, if I continue heating this mixture, guess what's going to happen? The product is just going to be this. Did you expect that, Max? You didn't expect that. All right, good. That means that didn't waste your time today. How did that happen? That was the intermediate, right, Max? Yeah. Now, when that does the 4 plus 2, I can do a retro 4 plus 2, because guess what? Another lesson here, guys. Heteroaromatic systems love more than anything in their life to be aromatic. So if there is a pathway to restore aromaticity, the driving force is usually pretty low to do that. So this will just do a retro 4 plus 2, and you'll drive this off. It's equilibrium. So it'll sometimes do retro 4 plus 2 to give you back that. It'll sometimes give retro 4 plus 2 to expunge acetylene, which can be driven off because it's gaseous. So eventually, over time, you're just going to exchange this substituents here for this one, because heterocycles love to be aromatic, and you've got the benefit of the gas being released. Now, pyrrole will do the same thing, but you usually have to block it. So usually people put a Tazl or a Bach, and you can get a Diels-Alder adduct too. Indole is just going to sit there and watch. Pyridine, maybe if the temperature is high enough, you might get a pyridinium adduct at nitrogen. That's known, but that's reversible. And that correlates with aromaticity. Big important one now is tautomeric structure. As Max said, the movement of protons from one place to another. You really need to know this, because it also affects the site of alkylation. So, Ren and Patrick, how often do you have regiochemical mixtures when you take indazoles, pyrazoles, and prazolones, and whatever, and treat them with base and an alkylating agent, or do Mitsunobu? Is this a problem that occupies your time sometimes, or any of your colleagues? Patrick says yes. All right, we have one taker. So at least at Pfizer, there's a problem. And actually, a very big problem. I get this problem all the time from people. And so understanding tautomerism is important because it'll also help you understand the regiochemistry of alkylation and how to control it. Let's first talk about the general issue. So here we've got a prototypical 2 heteroatom substituted pyridine. And you can have here the corresponding oxygen, nitrogen, carbon. And so the way I like to think about this in the case of pyridone, let's say, which is the dominant tautomeric form in solution. First, let's look at the possible tautomers that exist. So all of these structures are just related by the movement of a proton. You guys give me some thoughts on this? What do you say there, Zheng? Tell me this. Which one of these compounds is not aromatic?
That would be the fourth one.
Awesome. Not aromatic. So we can just get rid of that. Don't even think about that one for now. It's definitely not going to be a dominant one. Any other thoughts?
I would imagine it's like the difference between how, like the enthalpy between aromaticity and the C-double-bond-O.
You're favoring this structure here.
Yeah.
Yeah. Definitely a pyridone, that's what it looks like. It definitely prefers to be this form rather than this form. But is this one aromatic? Still is. I have p orbitals all over the place. This one is the one, as you correctly called out, not aromatic, because I got an sp3 lurk in there. Can't get any conjugation, so out of luck, that one. This one's also aromatic. And so what drives the solution, I mean, there's a few reasons why this one is in the pyridone form. Oxygen's very electronegative. And in solution also exists as a hydrogen bond dimer. Okay, so there's stabilization forces that are intermolecular as well. What about the case of this one? Amino Pyridine. You take it for granted. The folks in industry know the answer to this. I mean, this is, very rarely do people draw this in one form and not the other. We all take it for granted that 2-amino pyridine looks like that and not like that, right? Now, the reason for this also stems from your inherent knowledge from undergrad days on the pKa of phenol versus aniline and the electronegativity of the two atoms. So aminopyridines, they like to be in the dominant tautomeric form of the aminopyridine, whereas the 2-hydroxypyridines favor the pyridone form. Now, what about the case of carbon? Do you think 2-methylpyridine likes to be like that? People are laughing hysterically, right? If you're watching the video, you can't hear the hysterical laughter, but it actually exists. It's a very rambunctious crowd we have here at 8 in the morning. And so, yeah, 2-methylpyridine exists like that, but what is the effect of that methyl group? Does it make it more acidic, less acidic? Dongmin? Team pyridine. More acidic, yeah. Well, let's go all the way back here. Like several hours ago, we were talking about pyridine. And I said when I see a pyridine, I think of imine and a triethylamine and nitrobenzene. Well, if it's an imine, that means this should be like a methyl ketone. That's what when I see that, I just see methyl ketone. So I can use LDA, deprotonate, no problem. Can I use LDA to deprotonate that? You need a much stronger base, like almost like deprotonating toluene. Okay, great. So to do a little review of aromaticity, why don't we quickly look at problem of the day number 2, which hopefully will illuminate on the screen momentarily. Problem of the day number 2, we need a couple of volunteers there. Or maybe we can look at the structures of those compounds and find who the volunteers are going to be. Let's see. For the first one, we need help maybe from the benzanulated folks. So we've got some quinoline people here. How about, let's see, how about Hannah? And maybe some assistance from Sarah. There we go. So let's just talk about problem of the day number 1, the top row here. Organize the following molecules in terms of decreasing aromatic character. So we first need to identify which is going to be the least aromatic of these.
By analogy, probably the nitrogen analog.
Well, the analogy I would reach for is to go to your laminated sheet and go to the heteroaromatic, the aromaticity values, and think about, pretend the aromatic, because everything is equal, right? We just got 2 benzene rings fused into all these things, so the trend should be the same as if I just thought about furan, thiophene, pyrrole, and benzene.
analog is going to be the most.
That's our starting point. That's our boring benzene.
And so then probably they're already in order from most to least. Well, with the exception of C and D need to be flipped.
Yeah, that sounds pretty good. So what Hannah's saying is that the least aromatic is C. Then, oh, you're drawing it out. Okay. Yeah. Most aromatic, next most. Oh, thiophene versus pyrrole. Are we happy with that designation? I got a few people saying no. Maxie, what are you saying there? Vigorously shaking his head. His glasses almost fell off. What happened?
I assume because you stopped on that.
Zhang, what do you say?
Thiophene should be more aromatic because it has like extra d orbitals to stabilize the or to interact with the pyrrole.
Okay,
to
great.
stabilize the aromaticity.
So furan is least. That looks pretty good. TAs, are we good? All right, great. Okay, fine. How about the next one? Do we have a team thiophene? Let's see, where are these people? Oh, yeah. So how about Chuang or Gigi? This is an interesting one. The effect of annulation and where the annulation takes place. So which one do you think is the most aromatic? Where is Chuang and Gigi? Where are they? Oh, there they are. Okay, great. So, feel free to opine on this topic. Most aromatic. What do you say there, Gigi? You just give me general thoughts. By the way, in heterocycles, all forms of participation are encouraged. If you like to get up and do a dance, you can do that. If you like to raise your hand and say disparaging things about my outfit, encouraged. Anything that keeps people awake and excited, it's encouraged, and you'll get credit for it. But Gigi, anything to talk about on this one? Just tell us your general feelings.
I think C should be the least one.
You think C should be least aromatic?
Yeah, C should be the least aromatic.
Okay, that's a good call.
D should be the third one. And for A and B, I think A should be the most aromatic and B should be the third.
So you got this one. That's the most important thing to get, is that isobenzothiophene is the worst. But after that, these other aromatic rings are kind of bringing normalcy to the picture. They're bringing civility to the heterocycle. So this one is very aromatic. This one less so. And this one least of those three. And then worst. So most aromatic here. Then more aromatic. Then aromatic. And then this one's pretty disappointed with life. You don't agree, Saul? Oh, you do. Okay, good. I'd be in some trouble. So the question I often get, and let me ask the folks from industry, how often would someone in your company recommend the synthesis of, let's say, this compound? Oops. Isoindole. Have you guys... Nobody? Why not? Why you don't like that? It looks unhappy. That's enough. You know who recommends this? The computational folks. Sorry, Sal.
What?
Yeah. Why is it? The same rule. Remember we used a little rule over here on charge topological stabilization? We can talk about, the way I like to explain it is, you've disrupted the aromatic character here. You've just disrupted it, and as Patrick says, it makes it unhappy. That's perfectly fine. But if you're not satisfied with that explanation, here's another one. And it all comes down to thinking about the parent. So the parent of indole is indane. And if we want to make it totally accurate, we need to think about the indane anion. So if you do the computation, the indane anion is going to be happier here than here. And that's why indole is more stable than isoindole. That's your sort of high-level explanation for something which is intuitive to all of you. You all knew it. That was the first thing Gigi said, was, I don't like that one. So there's the reason. Oh, so med chemist, how do you take the isoindole and make it turn it into, it's like if the computational guy says, or gal says, make that, what do you put in its place? Indole sounds good to me. Happy. Happy compound. Why is it happy? Right over here, we talked about it. Remember over here? Pyrrole becomes happy with becoming imidazole. Same thing. You can take isoindole and turn it into a pretty happy creature. A lot of FDA-approved drugs with indazole in them. So indazole's happy. How about 2-hydroxyfuran? Now we have a pi-excessive heterocycle. It's not happy with life, and we've added a hydroxy to it. So, which of these tautomeric forms is going to be the most aromatic? And again, it's on to Sarah, Shuang, and Gigi. You know, we're going to call on you a lot today, but honestly, we don't do a lot of furan and thiophene in this class because drug discovery people just don't like them so much. So this will be the only class we're really picking on you. This much. Which one do you think there, Gigi? Which of these is aromatic?
The first is aromatic.
First is aromatic?
Yeah, and these two are not.
These two are not. And so if you had to vote, which is going to be the dominant tautomeric form in solution? Wrong! The third one, why?
Because it is more stable than the second one.
Okay, and I said wrong to the first one. So yeah, it's definitely good deductive logic there. And indeed that is the case, because this is so pi-excessive that it's just, it's fraught with unhappiness in its life. Do not propose, you can use 2-hydroxyfurans as intermediates in a reaction, but you do not want to use them, you wouldn't propose a stable one. Just like pyrroles are, unless they have electron withdrawing groups, if it's fine, right? Look at Lipitor, it's fine. You put electron withdrawing groups, it's fine. But, Patrick, at Pfizer, are they going to let you put pyrroles in the modern era in your structure? Big no-no. Does Lilly have the same rule?
Yeah.
They don't like them. Even you can say Lipitor all day and they still don't like them. Same thing. You can't put furans. You usually don't put thiophenes. Benzothiophenes sometimes. But it's rare. And often the thiophene and the benzothiopene, in the case of Plavix, we'll talk about one day, it's a prodrug. So as soon as you add benzothiopene to the body, it just gets popped open right away. And so, not very happy, not aromatic, but this one at least is conjugated. So that one is okay. And that's the dominant tautomeric form. Now let's take the lesson we just learned here to talk about the problem of the day number 3. So problem of the day number 3, it says, as a medicinal chemist in 2019, what would you view as a potential metabolic liability of Vioxx? So you can pass the iPad to someone. Who is it going to be? Any volunteers? Nobody needs coffee? You guys are just wide awake this morning, huh? Wired. You know, we used to have a coffee cart out here. That's why we brought it in here, because the coffee cart's gone. This is just to be nice to you folks. I'm paying for it. You want coffee? Take some. Anybody? All right. Who needs the iPad? Everybody looks down. Max to the rescue. Oh, we have, okay. Fantastic. All right, they're clamoring for it.
Oxidize at the
Tucker,
Yes.
what do you say there, Tucker?
I think it's probably
Are you drawing out there? Oh, yeah. Oh, you're just saying oxidation. Okay. Why? He says the answer is oxidation here. Why?
It's a CH bond and it's conjugated to everything else that seems to be pretty
Tucker,
radical.
Tucker, are you in, which group are you in?
Shenby?
Shenby. Okay. I thought when you said CH bond.
Are you on this committee?
I'm probably on all of your committees, okay? I mean, give me a break there, guys. I don't have any hair left, barely enough memory cells to teach this class. Okay. So, Tucker, you're saying oxidation,
Yes.
and you're saying how does that happen? Teach us.
You go to SIP. There's like
Oh, you think SIP is going out there for the action. Ah. Do you need SIP for this one? I need you to think more deeply there, Tucker.
Guess I'm not.
SIP, SIP is when biology brings out the big guns. You think she needs the big guns for this one?
Perhaps not.
Perhaps not. Tell me what other tautomeric form of this might exist.
You could go into the hydroxy pyridine.
Aha!
Oh, and then there's O2.
Maybe there's a fleeting amount of this stuff. And then you said O2. And then that compound can either disproportionate and give you the hydroxy product, or the ketone, or maleic anhydride. So in 2005, E.J. Corey published a tetlet paper where he took Vioxy, treated it with potassium terpetoxide, and then O2, and got these products. And in a sort of two-page tetlet said, oh, you folks at Merck might want to consider that the reason your drug failed or was pulled from the clinic was because of this. Now that's, if you talk to the inventor of Vioxx, they debate about that. They're not so happy with that. But that tetlet made CNE News. It might be the only tetlet in history that made it to CNE News. Just one experiment.
If you put 2 fluorines there, would that be metabolically stable then?
I would recommend not doing it just because usually fluorine's directly connected to non-phenolic oxygens, like to kick off HF sometimes. But we'll leave it up to Ren and Patrick. Would you put fluorines there?
For the same reason.
For the same reason. Okay. And so I remember, none of you were all, I guess, in grade school or something, but when Vioxx was pulled off the market, that was like a big deal. It pretty much, like if you look at for one watershed event in the industry that made everything miserable for everybody, it was Vioxx being removed for, toxicity, what they thought was toxicity reasons. The reason was people were giving doses that were way too high. They were doing indications that weren't necessary. It's still a really good drug. I had colleagues back then that would go to TJ to get the Vioxx because it was a really good pain reliever. They had arthritis or whatever, and they weren't selling anymore. And Celebrex, Patrick's compound, you need doses that are 10 or 100 times more. This was like 5 mgs was enough. And Celebrex is, we'll talk about Celebrex. That's like 300, 500 mgs, sometimes a gram a day. So, debatable why that's toxic, but one sort of explanation for it that has been proposed is that. And I think these days, probably because of that experience, a 2019 medicinal chemist would be unlikely to make a furanone as a lead candidate. But correct me if I'm wrong, Ren and Patrick. Pretty accurate? Okay, good. Let's take a look at this dichotomous behavior of a hydroxyazole. For instance, we've got this hydroxy isoxazole, and it exists in possibly 3 different forms. Any suggestions here from anyone? How about Khalid? Which of these is not aromatic?
The first one.
You think not aromatic or aromatic? Well, it's a good thought experiment to run through, but we've got pi electron here, 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 here.
Yes, it's aromatic.
Okay, so we're good on this one. How about this one?
Not aromatic.
You say it with some trepidation, but if we have an sp3 center there, you're right.
Oh, yeah, okay, yes.
It's all over. How about this one?
Aromatic.
Aromatic, because we got pi everywhere. Now, which one of these do you think is sort of the dominant tautomeric form?
Let's go with, let's say, the third one.
Third one sounds good. I'm not going to ask you to articulate exactly why, because it is a slippery situation. It is the dominant tautomeric form, but both are accessible when it comes to doing a reaction. So, for example, if I want to make these two acetylated, one is a benzoylated, one is acetylated, from the same starting material, let's just call it A. What conditions would I use for each of these to access this one versus the top one? Yeah, as Max said, it's all about the base. No treble. That would have been funny 2 years ago. Okay, so you use base or you don't. So for the top one, we're going to need base. And that will give us that. For the bottom one, we're just going to cook this fella up in acetic anhydride and wait. We will do this again and again. The folks from Lilly and Pfizer are probably wondering, how do you get regioselective attack on imidazole, pyrazole, indazole, random zoles? And usually it comes down to this type of paradigm. You do it under neutral or weakly acidic, or you do it under strongly basic, and you can get different types of selectivities. We'll look into it. Before the class ends, we'll go into another sneaky way to control regioselectivity known as the SEM trick. We'll get into that in just a minute. How about hydroxypyrazolones? It's the same type of rule govern this one as well. Jess, what do you think? Which one do you think is the dominant one? Yeah, middle one is good. And this one here, what is the product when we treat this with methyl iodide and heat? No base. Just in methanol. What do you say there, Hannah? Yeah. What's the significance of this? Well, I guess you should know, since we're going to talk a lot about medicines in this class. But that is the first drug. This is called antipyrine, and it was discovered by Sandoz in 1884 by Ludwig Knorr of the eponymous Knorr cyclization. It's marketed by Sandoz, and it basically just took fevers and it made them go down. No? So We good? Oh, okay. So antipyrine, if your kid had a fever, you take this, and the fever went down a little bit. Any ideas on how we make this starting material? We haven't talked about ring synthesis yet, but this one is so trivial looking. So methyl acetoacetate and phenylhydrazine, and you get out that starting material. Now you might be wondering, hey, why do we get that radioselectivity of the hydrazine addition? We're going to talk about that. I mean, if I tell you everything in lecture 1, you don't need to come back for the other 23 lectures. There has to be a reason to get you back. Okay, that's 5-member ring tautomerism. How about 6-member ring tautomerism? What do you say there, Cheng, on this top one here? Which one do you think is going to be the most happy in solution? A. Well, let's first ask you, Cheng, which one is aromatic? Good. Now, which one do you think is just sort of, which one's better looking? Yeah, A looks good. And anybody prefer B? Saul prefers B because he likes to be opposite of everybody. Or maybe he has a reason.
A CN pi bond is stronger than an NN pi bond, which is effectively what you traded.
There is that, and there's also a huge driving force of hydrogen bonding in solution. But definitely that is, the explanation you gave on the NN bond being sacrificed for the NC bond is true, but also you get a huge stabilization from hydrogen bonding for the same reason that pyridone is so happy. So hydrogen bonding can screw you up and give you a different prediction than you would have thought. How about this other one? Same? You still think, what did you say?
I'm not quite sure you're asking me or other people.
Yeah, sure. I'm always asking you, Cheng.
First, they're all both aromatic.
Both aromatic.
I think A is preferred.
You'd think A, right? Anybody, I mean, you'd have to be insane to think B. Anybody think B? B, Saul B again, of course. For the same reason Saul brought up about the NN bond and CC bond, yeah, B is actually the dominant tautomeric form, but I would argue that the hydrogen bonding component is even more energetically responsible for this phenomenon. So tautomerism can be quite sometimes unpredictable, unless if you remember this hydrogen bonding phenomenon. So really important when the computational chemist brings you structures like this, and they say, oh, I like this structure because it's got this nice hydrogen bond acceptor here. And you can go in and say, wait a minute, pal. It might actually be a donor. So can you recalculate that? Okay, how about these keto-type substrates? So in the case of pyridines and pyrazines, where X is equal to N, you actually favor that because of this nice hydrogen bond. So the enol form is favored. How do you like them apples? And when this is benzanulated, such as quinolines and quinoxalanes, it's favored. And that gets us to the sort of reason that we're all here today. Anybody here in Floyd's group? Except half of David's body is in Floyd, but he's a TA, so he doesn't count. The cause of genetic mutation is when the normal pairing, ATGC, so in this case you've got AT There's adenine, which is a purine. We're going to have a whole lecture on purines. They're a lot of fun. And this one is a pyrimidine or pyrimidinone found in thymine. Cytosine sometimes comes out for Halloween looking like thymine. So sometimes cytosine will look like this. And that's a bad day for your coding mechanisms. That's why mutation happens, one of the reasons. And when mutations happen, humans form from amoebas. It's all about tautomerism. So nature took heterocycles. Now, a useful use of tautomerism can sometimes be in new reactions that come up that take advantage of these types of pyridone and hydroxypyridine phenomenon. Now, the normal way of taking this isoquinoline and converting it to the corresponding nucleophile replaced analog is doing what? What would be the normal way of doing this? POCl3, Hannah, which is it's kind of like medchem table salt. They use it all the time. Right? Yep. Yes, the both of our industry folks are shaking their head. Indeed, POCl3 is really, really needed. But PiBrop, what's the structure of PiBrop? I mean, in case you forgot what the structure of PiBrop is, there's a very useful part of the book that actually has listed out all of the peptide coupling reagents that are known. So we can go to amide bond formation and skip over to this very useful section that's got all the crazy peptide coupling reagents out there. And mechanisms for it as well. So there's PiBrop. So if you take PiBrop and you treat it with the quinoline or isoquinoline, the tautomeric form that is the hydroxy version will engage the PiBrop, and you get an OPOPNR3 plus intermediate. And that intermediate is a great leaving group that can be mildly attacked with the nucleophile. You can use those PiBrop adducts in more than just SNAR reactions. You can also do Suzuki's with them. I don't know if you guys know about that, but it's a useful way of, in one pot, you take your isoquinoline or a related heterocycle that has a potential to have a small amount of the hydroxy tautomer in solution, activate it with the boronic acid and palladium, and you get the Suzuki product without doing POCl3, purifying the chloride, and then subjecting it to a second Suzuki reaction. Okay, questions? All right, great. So D, the facility of unimolecular reactions increases as aromaticity decreases. So in other words, problem of the day number 4. Looks like Max has volunteered for problem of the day number 4. Front row, Max. scroll down.
Scroll with 2 fingers. 2 fingers.
Oh, okay. Thanks. Wait on a second. Need a bit of an eraser there, yeah.
Yeah, there it is.
It's getting fancy with the colored chalks. Double espresso for him. Perfect. Great job. That's perfect. This type of thing would never happen with a more aromatic heterocycle. For example, I've shown on the board there the synthesis of duopyridine. So if you take pyridine, very low temperature, and you shine UV light on it, you will get duopyridine. The half-life of duopyridine is like 2 minutes. So it's been proven you can make it, but it's like duobenzene, right? Whereas these types of heterocycles are sort of, they're not really very aromatic. I mean, they're aromatic, but they could do without it. And so these types of rearrangements can happen. And we'll see these throughout the class. Any questions? Florida, any questions? We all good over there? Okay. Let's talk about the general reactivity of heterocycles with regards to their electrophilic attack at nitrogen. So as I remember, the people over there probably can't see anything. Is there a way to make this screen here show up on that? There is? Okay. That's probably needed. So there's really 4 types of nitrogens. This is really important to commit to memory, and it's got to be part of your instinct, the way you think about heterocyclic chemistry. You've got the pyrrole anion. You've got sort of pyrrole that's alkylated. You've got a pyridine nitrogen, and then you've got charged pyridine alkylated. That's it. Those are the 4 types. You can mix and match these and put them in an infinite array of different heterocycles. And their features are additive, as we'll see in just a moment. So pyridine, as we all know, forms tons of adducts. Pyridine can be oxidized with a peracid to make pyridine N oxide. Very rarely do pyridine N oxides appear in drugs. It's pretty rare. Most modern medicinal chemists will not put them in a drug or even propose them, but they are super duper useful intermediates. We will see them more. There's a whole chapter in the book on what you can do with pyridine N oxides. They're actually really useful. Pyridine acylium intermediates, we use them all the time. Anytime you acylate something with DMAP, that's the mechanism. Pyridine Lewis acid complexes, that's all the time. Where are all the Engel people, right? I mean, that's how ligands work, right? A lot of ligand design is based on that. And then you've got these strange, what they call zinc-A salts with the a dinitroaromatic attack there. And we'll talk about what these zinc-A salts do, but there are great inroads towards putting other things at nitrogen that can't easily be put by simple alkylation. All right, let's talk about the curious case of imidazole. So imidazole is a pyridine and it's a pyrrole, both. So when we add an electrophile onto imidazole, what happens? If you're an electrophile and you see imidazole, what are you going to do? But you're going too quick. You don't just go to C5.
Go into the nitrogen and then go into C5.
Okay, you're going to go into nitrogen. So if I put an electrophile on just a pyrrole, it's not going to react at nitrogen. But if I put an electrophile on pyridine, it's going to react to nitrogen. So imidazole has got both creatures here, and the only one the electrophile sees is that, which can then rearrange to give either, depending on the scenario, but most often, that. Now the tricky thing is understanding how to control regioselectivity in these systems. This is something that that people in medchem struggle with all the time. So let's imagine that you want to take an imidazole and we want to alkylate there. Can I just take phenyl, imidazole, and sodium hydride, and then the alkyl iodide, and be assured I'm going to get one regioisomer? No. So one thing to remember is that some atoms, heteroatoms, have a great effect because of electronics to direct the site of alkylation. So in the case of chloroimidazole, you almost always get exclusive or the dominant product being alkylation away from the chlorine. And then you could do your Suzuki coupling to put the phenyl there. That's one workaround. There's others. For example, this sneaky SEM trick that can be used in a variety of different contexts. One of them is imidazole. Because let's look at the CH bonds. This is a great preview for tomorrow and Wednesday's lecture. These two CH bonds, and indeed even, of course this one, all three of these are quite different. But let's talk about these two in particular. Whether this one is near a pyrrole or near a pyridine changes completely how these two things react. So when we put a SEM group on imidazole, that's a SEM, and we do some sort of lithiation or zincation or something and cross-coupling, we can get this adduct, because a pyrrole-like CH is going to be more acidic than the pyridine one. We'll talk about that, I think, Wednesday. But then let's imagine we want to open up the reactivity here. When you treat this compound with catalytic amount of SEM chloride, it does a magical dance. And the product of this is that. And what once was a pyridine-like CH is now a pyrrole one. Look at that. Any idea how that happened? And why you only need catalytic amount? You regenerate, so you must be regenerating some chloride. Well, what happens first? Tucker's looking like he wants to answer this one.
From the N adduct on the nitrogen, di-7. And that's tolerated for the polymer, or in resonance with the polymer of the nitrogen, or at this 6.5%.
And we're good to go. That's the thermodynamic product. Of course, it can go, again, it can keep equilibrating, but the thermodynamic product is that one. So it just eventually just funnels all to that. Now, we are pretty religious about staying on time in this class. Sometimes we go over, it's rare, and sometimes we go under. And when we go under, we put those minutes in the bank. We have a few minutes left, and so there is enough time to talk about problem of the day number 5. Probability number 5 is great because it's a great prequel for tomorrow's lecture. We have a thiazole. This is called the Dandoni aldehyde synthesis. In the modern era, not a very useful way of making aldehydes, but from the point of view of teaching heterocycles, it's a very nice, instructive mechanism. So problem of the day number 5. Do we have a thiazole team? I thought we had a thiazole team. Oh, yes. Zoe and Ziki. Where are they? Where's Zoe? Oh, there's Zoe. And we have Ziki. Where's Ziki? I don't see her. Okay. And you want to try, Zoe? No. All right. Do we have? Let's see. We have takers here. Who have we not? How about Vincent? What do you say there, Vincent?
I can try.
All right, great. I'm going to help you.
Okay.
So we're just going to take it elementary steps there, Vincent.
Okay.
What is he doing? Good. He's attacking. Okay, great. Great. Don't forget the TMS.
Yeah.
You're missing a phone charger.
On what?
No, Phil, you're just a cabinet.
Oh, thanks. All right. Now what do we do? You're attacking.
This oxygen to the carbon adjacent.
Go one over. We don't want to attack the carbon. That's going to be a problem for Baldwin.
Okay.
And geometrically is an issue.
Attack TMS. Sure.
To attack TMS. That's you got it. Great. Perfect. Now that's a very happy anion. It's a great preview for tomorrow's lecture because we're going to learn all about that. At least this week we're going to learn all about that. What makes anions happier than others? That one is a particularly happy one. Now what do we do with that? We need to eventually make a carbon-carbon bond, and that's not a carbon-carbon bond yet.
Does the whole group on nitrogen migrate over, or is there?
Well, I'm going to give you a clue. You're in a soup full of aldehyde.
Okay. So this attacks another.
Let's just do another one.
Yeah.
how do we go from there to the product, Vincent?
So oxygen attacks the TMS. And that pushes electrons here.
You got it.
Yeah.
Brilliant. Now, this is the Dandoni aldehyde synthesis, but I don't see any aldehydes. Or maybe I didn't squint enough. Nope. There's no aldehyde there. So how do I turn that into an aldehyde? T-bath. Well, when we say Dandoni aldehyde synthesis, what we really mean is that this is going to become an aldehyde because I've added one carbon. So T-bath is just going to remove our TMS group, and everything's just going to be sitting there. Now let's talk about oxidation state. This oxidation state, is it at the oxidation state of an aldehyde or an acid or an alcohol? It's at the acid oxidation state? So I have to take that thiazole and somehow turn it into the oxidation state of an aldehyde before I disembowel it and turn it into an aldehyde. So the first step of taking a thiazole and dismembering it to a aldehyde is treating it with methyl iodide. When I treat this with methyl iodide, where's it going to go? Nitrogen. So first thing that's going to happen is we're going to get this charged intermediate. Next thing I'm going to do is treat this with borohydride. What's going to happen with borohydride? Reduce where? Reduce the imine. Here. You can have a coffee too, Ken. And, you know, that's going to give us now aldehyde oxidation state. All I have to do now is get rid of this thing. So back then they used mercury, acetate. You can use PFA. It's ugly, right? I mean, you know, you don't want to do that today, but this is the Dandoni aldehyde. Actually, there's a Merck paper where many years ago they used it on process scale to make a sugar. So it's not like it was never used. It was actually very useful back in the day. Okay, so that leaves us with exactly 10 minutes to put in the bank. Tomorrow, class begins at 9 a.m. instead of 8 because I got to drop a kid off. And then Wednesday, we'll continue with general reactivity. So this week is probably the most important week not to miss just because we're going through all the general stuff. And, yeah, so see you tomorrow, bright and early.
Real quick, guys, if you're here and you plan on coming and you want to receive emails about the class, but you're not actually enrolled in the class, there's a piece of paper up here. If you could just put your name on it and your email address, that'd be great.
And for those who picked up the textbook from graduate office but didn't sign up, please let us know.
It's at 10.
Oh, okay.
When do we end up looking? No, it's not.
Probably not.
I'll never say that.
Like the notes, if I write it on my iPad, so it's still my handwriting.
No, you cannot think.
Okay.
You can do your notebook on the iPad and paper copy for exam. Like basically copy everything on paper.
Okay, but I can't.
But you cannot bring the iPad.
Well, no, yeah, but can I print it out?
Yeah. Oh, yeah. Okay.
Okay.
Yeah.
Okay.
Paper one and handwritten. So if you write it on the iPad and print it, it's fine. But you cannot like.
Yeah, I know I can't bring that.
You cannot copy book and print it. It has
Yeah.
to be written by you.
Yep.
Yeah.
Okay. Okay. Cool. Thank you. Yep.
Do you have a question? It has to do. Yeah, I mean this one's going to be the most aromatic.
Always. So benzene is always more aromatic than hetero.
Yeah.
Alright.
It mostly has to do with if you look at. I mean, it's not a great idea. These are a better idea than I do, but if you look at the handouts, and you could probably explain it by the specific heteroatoms you're adding. But if you look at just this, you're going to look at a roll. Percent. This is just percent of it, right? So we're going to think of it as per roll. Thiophene is going to be 45. Purines worse, right? So thiophene is going to be the most aromatic. Pearl is going to be next.
So we just look at the number.
Oxygen. Yeah. The better explanation is that sulfur is softer and it's bigger, and so it's going to act a little. It's not going to detract as much from the electronics of the ring as it would if it was something like nitrogen or oxygen. Basically, you can think of thiophene as like isosteer for benzene. In fact, the electronic maps are relatively similar.
Okay.
Sulfur is just harmless.
Yeah.
It doesn't hurt.
Because its electrons are so like loosey-goosey, so it can kind of take whatever shape the system is sort of asking it to take.
Okay.
I don't want to confuse you, but one thing I need to mention, for example, if you have naphthalene, that's not actually really aromatic. So if you compare naphthalene and benzothiophene, the benzothiophene, what's the thiol, whatever this one.
Yeah.
Compare this one and naphthalene, even though naphthalene has two benzene rings, and even anthracene has 3 benzene rings. This is more aromatic because anthracene and naphthalene, like two benzene rings unrelated to the original benzene, are not quite benzene. It's more like diene.
Would you mind erasing?
Oh yeah, sorry. Yeah, sure.
Okay.
Yeah, it's aromaticity is still really complicated, and we don't gonna trick you guys to make it sound like unless it's mentioned in the lecture.
Okay.
Yeah.
Yeah, thanks.
Free consulting.
No for you, please.
You don't know anything about
How do you activate this alkene selectively? Maybe I should put that. One day I'll do it as a joke. I'll come in.
What time do you have?
How early do you have to get in to put on the free consulting?
Oh my god.
It's at 10. I think I see you have 10. I just like to prep the chalkboard so I don't have to.
Is it mostly going to be on the chalkboard or will it be snoring?
It will be all blackboard and handouts.
Oh,
Wow, free espresso. They really stepped up the game.
You're going to have a hard time getting people to come to your class, Gary.
That's nice. So I didn't think about this to do the
You can see
the problems of the day up here.
Yeah, so we actually look at it. So the grad office set us up with an Apple TV.
That's
So we just hook it in.
okay, so it's basically all recorded.
everything is for it.
All and even
You
that.
just airplay.
So today we didn't have anything on this. We didn't
put an iPad to that. And so it just
but
shows
yeah,
up
if
there.
someone joins on it, we will.
So you can.
Okay.
So any Apple device I can do this.
Yeah, it should be. The thing that Phil likes about this is you can draw. So like people, this is like handwriting for somebody. So like he has someone like solve it in front of without
I want to do that, but I was just thinking it would save me a lot of time for just rewriting all of the problems of the day.
Yeah.
Maybe I'll ask Joe to come.
But it's pretty easy. I mean, if you're just going to put it up there, you can even do it from your phone.
Oh, okay. I'll ask Joe to come find you quickly.
We should have taken a picture of yeah, exactly. Oh shit. Well, next time.